which are specific in the sense that it's only made of carbon trivalent carbon. That means that carbon that are connected to three other carbons. Okay, so you have a carbon here, and it's connected to 3 other carbon. Okay, so you have to place somewhere a double link. Okay, between them. Okay, and you have to place exactly one double link between one pair and no more. Okay, each one has exactly one double link and no more. Okay, so the question is whether it's possible or not. Okay, so for instance here it's possible. Okay, and the question more than that in physics, what you want is that this configuration have to be stable. That means that you don't need to have just one configuration, you need to have a lot of them. In order to be stable, you need to have an exponential number of that. If you don't have an exponential number of valid configuration, where you have these double links which are disjoint and everybody has exactly one double link, then you know that the molecule is unstable. Okay? But studying that, if you look at the carbon as nodes, okay, what you're trying to do basically is to find what we call a matching. That means you try to match the vertices together, to match the vertices by pair, okay, such that everybody is matched and no one is matched twice. Okay, and studying matching is something that we know for a very long time in computer science, and there were recent progress in the algorithms of matching with application to chemistry. So let's go to the conceptual contribution. So the conceptual contribution is, came up with something that would look surprising to us. Okay, so for instance, in physics, they discovered that they can have group behaviors for clouds of birds without a chief. Okay, they can have some kind of global behavior without a chief. And this was quite a surprise for them. Okay, they like to broadcast it because they think that you have to take that into account. Okay, in your models at some point. Okay, so for instance, here is a bunch of results that I find quite surprising and might be irrelevant at some point. That means that if, for instance, if you're studying biology or studying some kind of gene networks or whatsoever, you may have to keep in mind that that to compute something, it may not require as much resources as you think, as much resources as you think. For instance, if you want to count up to n, okay, if you want to count things, okay, so you see people passing in front of you, okay, and you want to count them. How many memory do you need? Well, if you have n people, if you want to count exactly, you will need log n bits to do it. Okay, you will need, because if you don't have log n bits, you won't be able to count up to n consistently. Okay, so this is the intuition. Would randomness help? Well, it's unclear. Why would randomness help at some point? Would a random source help at some point in counting people passing by? It turns out that it helps a lot. Because when you have a random source, you don't need log n bit anymore, just log n is enough. So this is kind of surprising, and the algorithm is really easy. It's the following. So what you will keep in mind, basically, is I, and the number of people you will see will be 2 to the I. Okay? So you will count an approximation of 2 of the numbers, more or less, of the number of guys you see. Okay? So I is a random variable, okay? Because you have a random source. So what you get here is a random variable also. So now the question is, when I see somebody new, how do I increment my counter? How do I do? So what I do is very easy. It's just I remains the same, or is increased by 1. Okay? And I will get I plus 1 with probability 1 over 2 to the I. Okay, I will increment it by 1 with probability 1 over 2 to the I. Okay, and you can do the computations, and what you get is that after n increment, the expected value of 2 to the n of 2 to the I is n. Okay, or maybe it's minus 1 or plus or minus 1. Okay, but the spirit is here. Okay, so what is nice here is what is the size of I? 2 to the I will be of the size of n. So I will be of the size of log n. So the size of I will be of the size of log n. So to count up to n, you just need log n bits, no more. Okay, and you can increment your counter. Okay, and you will get an approximation. Which is nice is that you can improve this idea, okay, and still keep log n bit, okay, and compute an arbitrary close approximation of n. Very, very, very close, with a very, very short deviation. Okay, I mean, here we just have computed the expected value, but if you compute what's the name of it? The typical gap with the variance of it. The variance is n also. So typically you will be at square root of n of the value. Okay, so it's a very nice algorithm. So why should we care about it? Okay, you've got a nice algorithm which use a little bit of resources. Who cares? Well, who cares is the fact is that it's not just smaller, it's exponentially smaller. So if you imagine that you're in an randomly evolving environment, if you imagine that the biological systems are created randomly by selections and everything, what's going on? Here you have an exponentially smaller algorithm than the normal one that uses log n, counter or size log n. So basically, you can enumerate all these algorithms before having terminated writing the first one. There is an exponential gap here. But what I mean is that you can enumerate all the programs of size log n. You will enumerate all of them before having terminated writing the program of size log n. So if you imagine you're in an evolution-based systems, then this one has two advantages. It's smaller, consumes less resources, and it will be found before the first program of length log n will be written. So my guess is that this one has much more probability to exist in nature than this one. Okay. So I don't know if I've convinced you, but but this is why I believe that this is really important to be aware of that, because basically if you already reading gene networks is not easy, but if you don't even know this algorithm, you're screwed. There's no way you will be able to guess it. So well, this is the kind of stuff. So more surprising stuff is self-correcting codes. So in computer science we have a problem. Is that it's undecidable to verify that a program does what it's supposed to do. Okay, we know that because we don't even know whether it's possible to decide whether it stops or not. Okay, so we have to live with bugs. Okay, so some programs will be buggy, and there is no. We try to do our best, but there is no way, any way to verify.